Hello everybody, welcome to today's little presentation. My name is Professor Nigel Schofield. I'm at the University of Huddersfield in West Yorkshire, and I'm going to talk to you about electronic and electrical engineering. This is me. Academics always enjoy talking about themselves, so let's talk about me. My academic qualifications are, well, I have a Bachelor of Engineering degree in electrical power with honours, a PhD where my thesis was on the design of electric traction machines for electric vehicles, and I'm a Fellow of the Higher Education Academy. My professional qualifications then, I'm also a member of the Institution of Engineering and Technology in the UK, the IET, and through the IET I'm a registered chartered engineer with the UK Engineering Council. You are at the beginning of a journey, and my key advice to you is try to open doors and keep them open. Qualifications opens doors. A little bit about my background. I left school at 16 and I went and did an apprenticeship in the coal mining industry, and when I completed my apprenticeship, I then worked for 4 years as an electrician, but during that time I realised that the coal industry was in decline, and I realised that the qualification that I had as an electrician really constrained my career progression, and so I decided to go back to university. And although I'm going to talk somewhat about electrical power engineering, I want you to the examples I'm going to give you actually encompass all facets of electronic, electrical and communications engineering and other engineering degrees as well. So I'm going to give you a bit of a history tour, and then maybe we'll have a look at a crystal ball and say, where are things going in the future? Okay, so this is a steam power plant. Here's a building here containing 4 500 megawatt turbines and electrical generators generating 2,000 megawatts. That's only, it seems a large number, but that's only 3%, about 3% of the UK's maximum demand. Look at those towers there, they're for cooling of all the systems, and the stuff coming out of the towers there is just steam, it's just water vapour. But that pipe there, that tower there, the materials that's coming out of that tower are all the nasties in terms of things that cause emissions. And one of the key emissions that's driving a lot of policy and a lot of our engineering and society is CO2. And this is a coal-fired power plant, and so there's lots of CO2 emissions associated with the generation of this electricity. Now, when I graduated back in 1990, UK electrical generation by coal was about 65%. Remember, I told you I was a mining electrician, but also in 1990 the industry, the generating industry in the UK, was privatised, and very rapidly within 4 years after my graduation, electrical generation via coal had dropped from 65% to 35%. So you can imagine the impact that had on the coal mining industry. It had a great impact on gas generation because the deficit came from North Sea gas. That's in 1990 to 1994 then. Now in 2017, there was actually one day, there was one day when no UK electrical generation was completed by coal. And this was something that the National Grid was trialling just to see if that could be facilitated. And this was the first time since the start of industrial electrical generation back in the late 1880s. So you can think that the motivation for electrical engineering, electrical power, was all by coal-fired power stations right up until the 1950s, 1960s. And then we had some other mixes in the generation. This year, how much electrical energy will be generated by coal? You can have a look on a number of websites and you can see what is the generation mix in the UK. And then ask yourself, in 4 years' time, what will it be? So there's a lot of measures to reduce CO2 emissions on everything that we do. And electrical generation is heavily stacked in terms of CO2 emissions. And then think about what will the percentage share be when you are in mid-career. So maybe in 20 years time, when you've hopefully when you've graduated with a good degree and you're practicing engineering industry, what will be the electrical generation mix at that point in your career? This is another coal-fired power station. This is Ratcliffe-on-Soar near Nottinghamshire, and I'm interested in electrical power, and I drove past this power station in September 2019, only a year or so ago. Look, and what do you see? What's the difference between these two pictures? The difference was such that it made me pull at the side of the road and take this photograph. You see, there's no steam coming out of the cooling towers. There's no emissions coming out of the tower. What that means is this station here, which provided the base loading, continuous generation in the UK from the mid-1960s, the station is no longer generating. This is a similar design, again, a 2000 megawatt station. Okay, so no steam output. The station is effectively turned off, the first time since the mid-1960s. So if we look at electrical generation, this is when I graduated, look, 65% coal, about 16% nuclear, and then some other bits and pieces. By 2009, coal around about 30-35, combined cycle gas turbines around about 35, nuclear still around about 10 to 16%, and a little bit of green there, look, little bit of renewables. Fast forward 10 years then to 2019, and look at how renewables have increased. Renewables primarily here are solar and wind generation. We've still got our nuclear generation, we've still got our gas, but look how coal is reducing. In terms of CO2 generation, then gas and coal have to disappear. The government wants to get rid of CO2 generation, and if we look at projections going towards 2050, then we could see how gas will generally be phased out by 2040. Coal should be more or less. Coal is only really running now over winter load, peak loadings. But look at the expansion in renewables. Look at the amount of renewables we have to go from in now, effectively now, to 2050. This is your working lifetime. This is where you'll be working. I'll be retired, hopefully. And this is expanding areas where there are lots of opportunities. So electrification of many sectors of industry is key to decarbonising, and especially transport and heating in industry, heating domestically. Decarbonising them is going to be key going forward in the future. So there'll be new and rapidly expanding industries, and I encourage you to be part of them. Okay. If we look at a wind turbine system, I mentioned wind as a renewable. This is a 1 megawatt wind turbine, so we'd need 2,000 of those to replace that coal-fired power station if the wind is blowing constantly, 24 hours a day, 7 days a week, 365 days of the year. But the wind is not blowing constantly. It's very variable, up and down, and so we would need to install a lot more than 2,000 of these to replace that single 2,000 megawatt coal-fired power station. But this is what's happening. These are being installed. There are lots of places around the UK, particularly offshore, where we have quite a large supply of wind energy capability. And you can see that this is a little picture of a wind farm here, turbines offshore, and these are all connected electrically to this collecting point here. And on this platform here, there's all the electrical protections and switch gear, and then power taken off to offshore. Remember, I mentioned that the applications I'm giving you are all relevant to all aspects of electrical engineering. So think of these, the information from each of these wind turbines is actually being communicated to this central tower here wirelessly. And then all the information here, look at the antennas up here, look, all the informations, the controls for all of this wind park here. And there may be upwards of 300 to 400 turbines around this wind park. All of that information is collected and communicated offshore. So lots of requirements here for embedded systems, communications, electronics, both digital and analog, even in these power applications. And this is a new and rapidly expanding industry. Look at that time frame. It's going to take some time for all of this new equipment to be built up and assembled. What's inside one of those wind turbines? Well, there's an electrical machine. That's the things that I'm interested in. And then these switching devices here, these are power electronics. They might be switching 600, 800 amps at a few hundred volts. And these power diodes doing the same thing. So we're converting alternating quantities here, look, into DC quantities, or DC to AC. We're going vice versa. So if we look at a wind turbine, for example, there's the turbine blades, there's a gearbox that drives an electrical machine, and then we have a box of what we call a voltage source inverter, a box of electronics, all of these electronics here, converting this variable frequency, variable amplitude from the generator into DC onto a DC system. That goes down the tower, and then in the bottom of the tower there's another converter there converting DC into fixed frequency, variable current amplitude output to a transformer, which steps the voltage up from round about 690 up to 11,000 or 33,000 volts, and that then goes to the collection point and then offshore. A lot of electrical installation here and communications as well. Let's look at another example then. I mentioned that my PhD was in the design of these machines here that drive electric vehicles. And look at this machine here. Very early, the first road vehicles were actually electric vehicles driven by a battery. There's driving a motor, and to control the volts and amps to the motor there was this mechanical switching device here. It had about 15 kilowatts in terms of a number, 1900 lot. One of the big problems was the range of the battery. The vehicle could drive maybe about 10 miles an hour, and it had about a range of about 10 miles. So somewhat interesting, but not particularly reasonable distances. Fast forward to the future, look. So new magnetic materials, these are two magnetic materials, neodymium iron boron, samarium cobalt, invented actually. These elements were mixed into certain compounds round about the 1980s. They started becoming commercially available around about 1995, 2000. So really only 20 years old. That's revolutionized electrical machines. It means the machines, we can make them much smaller. We can make them fit into more compact places. We can make them more energy efficient. The switching mechanisms here has been replaced by power electronics, really reliable power electronics, only maybe 20, 30 years old in terms of industry. That's not a very long time. And if you look on this vehicle here, that lead acid battery would be totally useless for a modern vehicle. So new technology, nickel metal hydride, sodium nickel chloride, and lithium ion. Really, lithium ion, the batteries you find in your smartphone. That's the technology that's really moving, really allowing energy sources to be really compact and small, and moving our technology into new applications. Without lithium ion, this electric vehicle just would not be sensible. Fast forwarding now, look at a modern vehicle. This is the Nissan Leaf, and there's the battery system there. Look, it's sat under the vehicle. This engine compartment is now replaced with a new engine. They call it an electric engine, but it's a box of power electronics. It's that voltage source inverter, remember, that I mentioned, and that's converting DC from the battery into variable frequency, variable amplitude waveforms that drives the machine, the traction machine, and then that gives a mechanical output to the vehicle. And also when the vehicle brakes, this traction machine becomes a generator and charges the battery up, so we can recover some braking energy. We can make the system more energy efficient. Let's look at the battery. There's actually about 3 different sections to this battery, and inside the battery there's about 3,000 to 4,000 equivalent smartphone batteries there. and all of those batteries have their individual electronic control to manage their voltage, manage their state of charge. So that battery volume, I would say about 20% of that volume there is taken up by electronics that manage the battery system itself. And those electronics are controlled by a microprocessor, a dedicated battery management processor, and that battery management processor reports to a main vehicle management processor on the electric vehicle. So there are a number of embedded systems in terms of microcontrollers, microprocessors around the vehicle. Look at the power electronic converter. This is the box that converts DC to AC. These are the power switching devices. Sat on the top of there's an analog, digital to analog circuit board there, and that little black square in the middle there, that's effectively like a Pentium processor that sits in your tower computer or your laptop. That's effectively a computer there controlling the power electronics, a computer embedded into some power stage. And this system then communicates via, it's actually a wired communication, but in the future this could well be a wireless communication system. So on this one application, this one electric vehicle application, all of the courses that we deliver, electronic and electrical engineering, communication engineering, computer systems, look at the computing required on here to program everything, and electrical power, thermal and mechanical courses are all embodied in this one single application. So when you're looking for jobs, when you're looking at thinking where do these degrees take me, then if you look into industry, you'll see that more and more things are becoming what we call more electrified. And these are new. This is a new and rapidly expanding industry. One of the things that's restricting the development and takeoff of this industry is the lack of engineers qualified in these subject areas. So the potential is there, the challenge is there. If you're interested, come and get your degree. This is another example of converting power. Here we've got a DC to DC conversion, just an idea of some circuit elements, passive elements, inductors, diodes, capacitors, but also active elements. These are switching devices. These are MOSFET devices, which will be switching at quite high frequency, maybe of certainly megahertz, something like that. Switching at high frequency to keep the volume of these inductors down. Yeah, all of that pushed together onto a printed circuit board. Look, laid out. That's a design and for testing. And these DC to DC converters vary from microwatts up to megawatts. Gives us high energy conversion efficiencies. That's what we're striving for, huh? The conversion ratios and the high energy conversion efficiencies. Another example of an embedded system here. There's a car there. Look, this is a student project actually. Look, and connected on top of that car is a microcontroller that controls the features of the car. So the driving, the steering, some lights, and that's controlled remotely via this little processor here, a wireless connection to a mobile phone or a tablet. Yeah, this is an example of what we can do here. It's a little toy that we can control, but expand that up to an industry application, and you can see the power of more and more embedded controllers and wireless type communications. And here's another example of some of the complexity, if you like. There's a processor. These input-output signals here are around about 3.3 volts, but we may want to input some higher voltage, maybe up to 15 volts. So again, DC to DC conversions. There's analog to digital conversions on this circuit board here. And this is something that you should be able to attempt as you get towards the latter stages of your degree course. Yeah. And higher frequencies. 5G is an area of communications that's really expanding at the moment. And this picture here is showing you some software that's looking at the design of circuits that operate at high frequency and their packaging into compact compact components. Again, a new and rapidly expanding industry. Engineering is generally about working together on solutions. So on a degree course, you'll undertake your own individual project, but you'll also work as part of groups on group projects and teams. And some of the modules that are taught are to give you that professional development in terms of working with other people, understanding timelines, understanding how to work coherently as a team and with colleagues, doing your own individual element of work and contributing that into a team solution there. And if you do our MEng options, then in the final year of the MEng, you'll be involved in one of our MEng group projects. We currently have 3 main projects. This is the Formula Student Racing Car. We have a hybrid electric train, and then some drone systems. So these are a mixed bag of students across mechanical, electrical, energy engineering. You need that mixed competency in terms of undertaking these tasks, and you have to deliver something. This is not just about technical solution, it's about delivering a product to time and to some performance. These drones, for example, they will carry a payload representative of maybe some food supplies or medical supplies. They will fly for a certain distance and land in a certain remote place. For example, in an earthquake region, or if there's been a fire in a certain region, you can send materials in to help people remotely. All of our courses are underpinned by IET accreditation. So remember, I talked about my academic qualifications, and then I mentioned my professional qualification. So to become a professional engineer, you need to satisfy the academic requirements for professional engineering status, and to do that, it's always easier if your courses are accredited. All of our courses have just been accredited for the next 5 years in electronic and electrical engineering, accredited by the IET. Also, as part of the IET, we have an IET on-campus group. It's one of the few in the UK. This is a totally student-driven body. They organise external guest lectures, have industrial visits, and they have social and networking events. In terms of our electronic and electrical engineering courses then, these are a mix of different specialisms: electronic and electrical engineering, electronic engineering, electronic and communication engineering, electronic engineering and computer systems, energy engineering and mechatronic engineering. These latter two are linked in with mechanical engineering, whereas these first few here generally have a common first year. So what happens when students come into the university, quite often they may not be sure what's the real flavour that they of engineering, electrical engineering, are they interested in. So we have generally a pretty common first year across 1, 2, 3, 4 of our courses, and most of computer systems is common to our first year modules. And then by the second year you can then digress into the areas either straight electronic, or if you're interested in electronic and power, or if you're interested in communications, for example, or computer systems, then you can specialise in your second year and your final year BEng, and if you stayed to do an MEng, then you would be specialising in specific modules then. Okay, and you see we offer both Bachelor of Engineering and Master of Engineering. In terms of accreditation and professional engineering, if you want to be a chartered engineer, then the MEng qualification satisfies the academic requirements for chartership. If you want to, if you do a BEng, then our BEng satisfies you for the academic requirements for incorporated engineer. Okay. And if we look at where do people go, we have a number of organisations that take our graduates. In third year, or the year between second year and final year of BEng, what we call a third year. That's an optional placement year, and we encourage students to take a placement in industry because it gives you a year's worth of experience on your CV. These placements are employed positions. They're paid as junior engineers, and you'll be working with typically one of these companies or many companies. These are just a few of those that have taken our placement students, and that gives the company an extended interview of you, if you like, but also you an extended interview of the company, and also very importantly, it gives you a feel for really what you might really want to do when you ultimately graduate. And what we notice is when students then come back into final year for BEng or fourth year for the MEng from a placement, they are really more turned on in terms of their understanding of where they want to go once they graduate. And if we look at roles, these are just a few of the roles here that you might take up in a couple of years after graduating from your degree, from senior product engineer, component development engineer, procurement engineer, commissioning engineer, engineering design manager. So you may well become a manager. Once you've worked on projects for a number of years, then you start managing larger and larger teams. And a lot of companies take graduates on as junior engineers, but then gradually progress them, fast track them through their organisations in terms of project management. So I'm sure you've got plenty of questions. I'm sure I've not answered everything. Hopefully I've given you I intended to give you a bit of an overview of my career and how it changed about a bit, but it was allowed to change about a bit because I had the qualifications under my belt to facilitate that. So that's my piece of advice to you is try to get the qualifications. When I graduated in 1990, I expected that my degree would last me a lifetime. Things have changed so rapidly and things are changing so rapidly that I guess anybody who's graduating now will probably be coming back in a few years' time to refresh themselves on new materials, because materials are changing rapidly year on year. So it's a race. You have to keep up to speed. You have to get that technology under your belt, and that's the way to progress in your careers. Well, I hope you've enjoyed the talk. Please get in touch with us if you're interested in coming to Huddersfield. We need you as part of our team. Okay then, thank you, bye-bye.